Welcome to MathGPT. Today we're going to learn about a powerful mathematical tool in physics called commutators. Commutators play a fundamental role in both classical and quantum mechanics, especially within the Hamiltonian formalism. Let's start with the basic definition of a commutator. In quantum mechanics, the commutator of two operators a hat and b hat is defined as a hat b hat minus b hat a hat. This is typically written using bracket notation as shown here. Let's visualize what commutators mean physically. Imagine we have two operations, operation A and operation B. If these operations commute, then performing A followed by B gives the same result as performing B followed by A. In this case, their commutator equals 0. However, if the operations do not commute, then the order matters. Performing A then B gives a different result than B then A. In this case, their commutator is non-zero. The most famous commutator in quantum mechanics is the one between the position operator x hat and momentum operator p hat. This commutator equals I times h bar, Planck's constant divided by 2 pi. This non-zero commutator is directly related to Heisenberg's uncertainty principle, which states that we cannot simultaneously know both the position and momentum of a quantum particle with perfect precision. The uncertainty in position times the uncertainty in momentum must be greater than or equal to h bar divided by 2. Now, let's see how commutators relate to classical mechanics. In classical mechanics, the analog of the commutator is called the Poisson bracket. For two functions a and b that depend on position q and momentum p, the Poisson bracket is defined as the partial derivative of a with respect to q times the partial derivative of b with respect to p minus the partial derivative of a with respect to p times the partial derivative of b with respect to q. If we have multiple degrees of freedom, we sum this expression over all coordinates. Historically, when physicists developed quantum mechanics, they noticed that commutators behave very similarly to Poisson brackets. In fact, there's a direct relationship. The commutator is equal to I times h bar times the corresponding Poisson bracket. Commutators are essential for understanding how quantum systems evolve over time. In quantum mechanics, the time evolution of an operator a hat is governed by its commutator with the Hamiltonian h hat. This is the Heisenberg equation of motion. The time derivative of a hat equals 1 over I h bar times the commutator of a hat with the Hamiltonian, plus the partial time derivative of a hat if it has explicit time dependence. Similarly, in classical mechanics, the evolution of a function a is given by its Poisson bracket with the Hamiltonian. This parallel structure highlights the deep connection between classical and quantum mechanics. Let's work through a concrete example, the commutator of position and momentum. We want to compute the commutator between the position operator x hat and the momentum operator p hat. In the position representation, x hat is multiplication by x, and p hat is negative I h bar times the partial derivative with respect to x. Let's compute the commutator. First, x hat p hat acting on a wave function psi. This gives us x times negative I h bar times the derivative of psi with respect to x. Now for p hat x hat acting on psi. This is negative I h bar times the derivative of x times psi with respect to x. Using the product rule, this equals negative I h bar times psi plus negative I h bar times x times the derivative of psi with respect to x. Subtracting the second result from the first, the x times derivative terms cancel out, and we're left with I h bar times psi. Therefore, the commutator of x hat and p hat equals I h bar times the identity operator, which we typically write simply as I h bar. Let's summarize what we've learned about commutators. In quantum mechanics, commutators tell us how operators interact with each other. When two operators commute, their commutator is 0. They can be measured simultaneously with arbitrary precision. In classical mechanics, Poisson brackets play an analogous role. The canonical commutation relation between position and momentum is fundamental to quantum mechanics and leads directly to the uncertainty principle. Commutators are not just mathematical tools. They reveal deep physical truths about the structure of reality at the quantum level, where position and momentum cannot be simultaneously determined with perfect precision, unlike in classical physics. Thank you for watching this MathGPT tutorial on commutators.